Okay, so this is a sort of introductory thing to alternating current, AC, some of the terminology that we use around it, and some of the base relationships. So AC, sort of start with how it's generated, kind of what makes it what it is. To generate AC, essentially what you do is you whack a coil inside a magnetic field, like between the poles of a magnet, and you rotate it. You rotate the coil, or you rotate the magnet, either way, because that generates a changing flux, so it induces an EMF. So if we put a coil, I'm saying here I've got a coil with an area A and a number of turns N, and you rotate it with an angular velocity inside the magnetic field. Okay, so we're going to look at that situation a bit more. It's a simplified version of like what a real generator would be like, but it's the basic principles work. So we're going to look at that. So if we look at that side on, this is the coil side on, this is the coil's flat rather than at the vertical like it was in the other diagram. So we've got the coil side on with the area A and the number of turns N. It's inside a magnetic field with strength B, and it's rotating with an angular velocity. Okay. Now, if we take it that it's rotated a certain way, at that point there's no flux, but if we rotate it a certain angle, there will be some flux, there's some magnetic field passing through that coil, but not as much as there could be if it was like that completely at 90 degrees, then there'd be maximum flux. But we're going to use that this setup to like investigate the generation of electricity and what happens. So if we take that situation and we look at the flux, so the total flux through that coil is going to be equal to the magnetic field strength times the area. Now that's the perpendicular area, the area that's perpendicular to the magnetic field strength. And because at an angle like that, not the full area is being enclosed, and multiplied by the number of turns. So each loop will enclose that amount of flux. So multiply by that. The perpendicular area is just going to be the total area of the coil multiplied by the sine of the angle theta. So when theta is 0, the flux is 0, and then when theta is 90 degrees, the flux will be at its maximum. So we can write it as that's B times A times N times the sine of the angle theta. And because this is rotating with an angular velocity omega, we can represent theta as the angle that is turned through in terms of omega by replacing it with omega t. Okay, so it's BAN times the sine of omega t. Now, if we want to look at the voltage that this induces, we've got to look at Faraday's law. Now, I've written Faraday's law in the sort of calculus terminology here, but it's normally written in physics exams. It's probably in CA particularly, you'd be used to seeing it as delta phi over delta t, but it means the same thing. It's a change in flux over a change in time, just a slightly different terminology. So using Faraday's law, we can then plug in that expression for flux just above, BAN sine omega t. So we're doing the time derivative of BAN sine omega t. Because the magnetic field strength, the area of the coil, and the number of turns are all constant, we can take them out the front. So it's minus BAN times the time derivative of sine omega t. So the derivative of sine is cosine, and we have to apply the chain rule because it's a function of a function. So it's going to be cosine omega t and then multiplied by omega. So we're going to end up with an expression like this. The induced EMF is minus BAN, the magnetic field strength, times the area, times the number of turns, times omega, the angular velocity, times the cosine of omega t. Now, that expression in itself is not actually one that, especially in NCA, that I wouldn't expect to see that come up. But the reason that is important is that it does show that that gives a sinusoidal, the fact that there's a cosine as part of that means that if you were to plot the induced voltage over time, what you end up with is a plot like this, okay, where it has a maximum voltage of BAN omega, and it's negative, is a minimum negative BAN omega. So that's basically how we generate AC, is by putting a coil inside a magnetic field and rotating it. And by doing that, we end up with the sinusoidally oscillating voltage that is produced, which we call AC. Okay. Now, there's some tricky things about how we quantify this and how we the terminology we use. So, for example, in New Zealand, the domestic power supply we say is 240 volts AC, but what does that actually mean? Well, if we look at like the graph we just had, just sort of indicating the maximum and minimum voltages there, one thing you might assume was that, well, 240 volts AC means that the peak is 240 volts. So you'd have a maximum at the top of 240 and a minimum at the bottom of minus 240. That would make perfect sense. But the actual peak voltage in New Zealand is actually about 340 volts, like 100 volts higher than that. So it's not actually that. There's a different. Could it be an average? Okay, is the average voltage 240 volts? Well, no, because anytime you have a sinusoidal oscillation like this, there's an equal amount of time spent with a voltage above zero as below zero. So over a complete cycle, the average is zero, regardless of how big the maximum voltage is. If it's, like in this case, a maximum of 340, a minimum of minus 340, that averages out to zero. If it was a maximum of 1 million and a minimum of negative 1 million, it would still average out to zero. So it's not, it isn't a case of being peak voltage, and it's not a case of being average voltage. So what we're actually doing is we use the term, the voltage we describe, the 240 volts, is the voltage that would provide the same power as DC voltage of 240 volts. So 240 volts AC provides the same average power as 240 volts DC. That's so we can sort of compare them. Basically, that means if you have a light bulb, the same light bulb, and you plug it into 240 volts AC and a 240 volts DC, it should be the same brightness. That's the idea. Okay. Now, that value, that sort of gives that provides the same power, we call that the RMS voltage. RMS stands for root mean square, which means the square root of the mean of the square. It's kind of a mathematical way of averaging something to get a meaningful measurement. It's not the average, but you can kind of think of it kind of a bit like that, when the average is actually zero. So if you wanted to average the sine wave here, for example, this is also negative cosine, but any sinusoidal thing, if you just averaged it, it would be zero. But if you made it all positive, one way to make it all positive is to square it. You could then, so you square it all first, then you can take a mean because it's all positive. You're not going to get, it's not going to cancel out. And you're going to get a number. But that number is an average of a square, so the next thing you have to do is take the square root of that to get it back down to the right scale. So you're taking the square root of the mean of a square, which root mean square comes from. Okay, so RMS, it's not the average, but it kind of, we use it kind of like an average. So let's have a look at power in an AC circuit, because that's what ultimately we're trying to deliver, is the same power. So if we look at this simple circuit, so we're just looking at simple resistive circuits at this point. Okay, so we're not going to look at circuits that have capacitors or inductors in them at this point, because they have interesting behavior in AC circuits. So if we look at what the voltage does over time, we have sinusoid like that. I've shifted the start point for this. We had a negative cosine before, but we can start from anywhere in that cycle. So I'm just going with sine at this point. That has a maximum voltage. Now, this is can be, we can find the voltage at any instant in time from that using an equation like this: V equals V max sine omega t. I'm not going to go into too much explanation of this, but this is very similar to the formulas for displacement in simple harmonic motion, where the y equals a sine omega t. So it's y equals the maximum displacement times sine omega t. This is the voltage, is the maximum voltage times sine omega t. Okay. And just because it's useful, just remember from mechanics that omega 2 pi divided by the period is equal to 2 pi times the frequency. In a AC circuit, we would usually use 2 pi f because usually we talk about frequencies with AC electricity. Okay, so that's what the voltage is. So what would the current look like? Well, if we think about Ohm's law, current is equal to resistor voltage divided by the resistance, which means that current is proportional to resistor voltage. Now, this is true in AC just as for DC. So that means that when the resistor voltage is 0, the current is 0. So it will start at the same place. And when the voltage is maximum, the current will also be maximum. So the current and voltage, current and resistor voltage, I should say, are always in phase, which means they always have the same shape. And they're always at 0 at the same time, and they're always at a maximum at the same time. They're always at the minimum at the same time. So we get the same shape out of those. And we can write an equation based on the maximum current for the current at any given time, just like we did for voltage. Okay, but what we're interested in finding out, because we want to look at what happens with power. Now, in an electrical circuit, the power is given by current times voltage, I times V. And we have expressions for both I and V in terms of I max sine omega t and V max sine omega t. So we can calculate the power at any instant in time by multiplying those two expressions together. Now we've got I max and V max, and we've got two lots of sine omega t. So we can write that as that the power is equal to I max V max times sine squared omega t. So that's the square of the sine that we're putting in here. And I max times V max, we've got the maximum current times the maximum voltage, or current times voltage is power, and maximum current times maximum voltage is maximum power. So we can write that as power is P max times sine squared omega t, which is similar to the voltage and current equations, except it's got a sine squared term in it rather than just a sine term. Now that's important because when you plot sine squared, what you find is that you get a maximum power and it looks like this. So it has two important differences from the voltage and current ones. First of all, it's all positive. That's very important because we can't talk about average voltage or average current meaningfully because it's always 0. But we can talk about average power because it's always positive. There is an average value of power, non-zero. Okay? The other difference between the voltage, current, and the power ones is that the power has twice the frequency. So for the power peaks twice for every cycle of voltage and current. Because when you've got a positive peak of voltage and a positive peak of current, you get a positive peak of power. But then when you've got the negative peaks, or negative troughs, okay, you've got a negative voltage and a negative current. When you multiply those things together to get power, a negative times a negative gives you a positive peak again. So you're getting always positive peaks. So if you've got, like in New Zealand, 50 hertz voltage and 50 hertz current, you've got 100 hertz power oscillation because it peaks twice every cycle. All right, so we're going to look at that power a bit more. So the RMS, which is like an average, but it's not the average, but we can think of it like that. So if we have our maximum power along there, we can calculate the maximum power by using, this can be expressed as the maximum current times the maximum voltage. Now the average power is going to be half of that, okay? You can kind of think of it if you were to there are periods here where the power is above the average and there are periods when it is below. If you were to cut off the top half of the graph, it would exactly fill in the troughs. So it would all be flat along that average power line because of the symmetry of the shape of the curve about that point. So the average power is always half of the maximum power. And we can express the average power as the RMS current times the RMS voltage, because that's where we want that's the one we're interested in, is what the RMS, or the average power is the one that has to match the DC. Okay, so if I express it like this, just rearrange it slightly, I can say that the maximum power is double the average power. And I can express maximum power in terms of Imax times Vmax, and that's going to be double, because we know it's double the power, the RMS values multiplied together. Now, I can take Ohm's law. Ohm's law still applies. In this case, I'm going to take here, and I can replace the currents with voltage over resistance. It's just I've got to use the correct one. So for the maximum current, I'm going to replace it with maximum voltage divided by resistance. And for the RMS one, I'm going to replace it with the RMS voltage divided by resistance. So you get an expression like this. Okay. Now on each side, we've got, on the left, we've got Vmax times Vmax, so we can write that as Vmax squared. And on the left, on the right side, we've got VRMS times VRMS. We can write that as VRMS squared. They're both divided by resistance. That can cancel out. And we're left with Vmax squared equals 2 VRMS squared. We can take the square root of both sides, and we're left with this expression for RMS, that the maximum voltage is the square root of 2 times the RMS voltage. Okay? So there's that scale factor of the square root of 2. Okay? You can do a similar calculation for current, like instead of in that step there where I replaced the current with using Ohm's law, I could have replaced the voltages and put them in terms of current. And you can do the same thing and show that the maximum current is also the square root of 2 times the RMS current. So the scale factor to go between RMS and maximum values is the square root of 2. You can use Ohm's law with either maximum or RMS values, but not both together. So for example, you could use that the RMS voltage is the RMS current times resistance, or that the maximum voltage is the maximum current times resistance, but you can't mix and match between them. And just so, just for clarity, like if you're doing assessments and questions and stuff like that, the rule of thumb is generally that unless it clearly states otherwise, all voltages and currents in AC circuits are RMS values. So if it just says voltage, assume that means RMS, unless it says something like the peak voltage or the maximum voltage or something like that. All right, so an example. Let's say we've got a circuit like this. So we've got a 240 volts, 50 hertz power supply, such as we have in New Zealand, and it's connected to a 470 ohm resistor, and we've got a voltmeter and an ammeter to tell it what's going on. So let's go through some things. So first question here, what's the peak voltage and the peak current? So if I just bring up, so the peak voltage, well, we've got there the RMS voltage already, but we know that the peak voltage, or the maximum voltage, is the square root of 2 times the RMS voltage. So that's the square root of 2 times 240 is 339.4 volts. So basically 340 volts, like 100 volts higher. Okay. To find the maximum current, or the peak current, is going to be, now there's a couple of ways we could do this, but we could just use Ohm's law, okay? Just use voltage divided by resistance. I've got to be careful on which voltage I use here, okay? If I'm finding the peak current, I want the peak voltage, okay? So I could go 339.4 divided by 470 is 0.772. Right, 772. I forget that right. 722. Okay. There's another way I could have done that, which is basically the same calculation, just in a different order. I could have done the RMS current by doing the RMS voltage divided by resistance, which would be 240 divided by 470, which is, just checking on my calculator, is 0.511 amps. And then I could go, the maximum or the peak current is the RMS times the square root of 2. So 0.511 times the square root of 2 and get the same answer. Those are basically the same calculation. In both of those cases, I've used Ohm's law and I've multiplied by the square root of 2. I've just done them in different orders. That's fine. Okay. So that's the peak voltage and peak current. So what if I wanted this one? Calculate the current in the circuit at a particular time. Okay, I'll just change it to a different colour to keep it clear. So B. Current in the circuit at a time of 0.437 seconds, and I'm assuming that supply voltage is 0 at time equals 0. That just means that makes it a sine curve. So I can use this relationship, I equals Imax sine omega t. Now the first thing I'm going to need to do is find omega for this. Omega is 2 pi f. So 2 pi times 50, which is equals 100 pi radians per second. Now, I'm actually just going to leave it like that. I'm going to leave the pi in there because it's not an answer. I'm using it as a calculation step, and it's easier to write that way. So, if I want to calculate the current, I know all these things now. I've actually calculated the maximum current already. That was in the previous question. That was 0.722 times the sine of 100 pi. That's the omega, and the time is in the question, 0.437 seconds. And if we plug all that in, now making sure when you do that, your calculator is in radians mode, we get a current of minus 0.584 amps. So that's the current at that instant in time. So it's negative, meaning that there's a positive. So remember, the current is flowing back and forward. So it's flowing in whatever the backwards direction is at that point. Okay. And the third part of the question, calculate the average power output by the resistor. So again, there's a couple of ways of doing this. I'll show them both. First of all, I would just do this, given that we've already actually figured out the RMS current, you could just do this. The average power is the RMS current times the RMS voltage. We already have those numbers. The current was 0.511, and the voltage was in the question, 240. So the average power was 122.6 watts. Okay, that's one way of doing it. The other way, a little bit more calculation in this one, you could find the maximum power, which would be the maximum current times the maximum voltage, which would be 0.722 times 339.4 is 245.1 watts. That was using unrounded values in the calculation. And then know that the average power is the maximum power divided by 2. So 245.1 divided by 2 is 122.6 watts. Those are both perfectly valid ways. I would have done the first one, given that we'd already found the RMS values. It's obviously shorter, less calculation involved in that one. Okay, so moving on. Just a quick summary of the basics here. We get a sinusoidally oscillating voltage from basically rotating a coil inside a magnetic field to get a changing flux. We can express the voltage at any point in time using this expression similar to simple harmonic motion. The voltage is the maximum voltage times sine omega t, remembering that omega is 2 pi divided by the period, or 2 pi times the frequency, probably more useful in AC. We have a similar relationship for current, where the current at any time is the maximum current times sine omega t. For power, if we figure that out, because it's the two multiplied together, you get an expression that's all positive, a curve that's all positive. It has a maximum power, and the average power is half of that. Okay, so you've got your maximum power is double the average power, and if we use that to calculate the RMS values, you get an expression that the maximum voltage is the square root of 2 times the RMS voltage, and the maximum current is the square root of 2 times the RMS current. You can use Ohm's law in AC just like you can in DC, just you've got to make sure that you use the correct one. You either use RMS values together or you use maximum values together. You can't mix and match RMS and maximum values. You can't use them together. You've got to use one or the other. All right, so that's the introduction to AC. Hope that's helpful.